Hello everyone, I'm back from the C department of UIUC and I'm going to present you our work, RED-PSM, Regularization by Denoising of Partially Separable Models for Dynamic Imaging, with my advisor Joran Brester and Mark Lasky. Although the proposed method is applicable to different dynamic imaging problems, the focus is on dynamic tomography. The dynamic tomography addresses the recovery of a time-varying object from its projections acquired sequentially at specific times. The problem arises in many different fields. Since the object evolves in time and too few projections are required at any time instant, only one in the extreme case, they are insufficient to reconstruct the object at any time, making the problem severely posed. The acquired data are the set of projections G obtained with uniform time sequential sampling using the radon transform. If the object was static, it could be reconstructed using filtered back projection. However, inconsistent time sequential projections lead to severe artifacts. The following points motivate our work. Using more accurate spatial priors for dynamic imaging problem leads to improved reconstructions. The ground truth dynamic object data for supervised learning is either non-existent or very scarce. Also, existing methods are not easily scalable, and they do not include a convergence analysis. A key component of our work is the PSM, which is the representation of a dynamic object by a series expansion of k spatial and temporal basis functions. PSM introduces a specific low-rank structure. It's parsimonious and interpretable. The other key component of our work is the regularization by denoising method. RED is a recovery method using an image denoiser D in the following regularizer row. The analysis of RED is enabled if the denoiser is differentiable, locally homogeneous, and strongly passive. Then, RED satisfies the simple gradient rule. Our proposed variational formulation to estimate the dynamic object F is composed of a data fidelity term using PSM with the radon transform operator, Frobenius norm penalties to prevent PSM factors from growing without limit, and RED spatial regularizer. Since using PSM in RED does not allow efficient propagation of the updates on PSM to bilinear components lambda and psi, we perform a bilinear variable splitting and apply RED on the full rank representation F. To solve the resulting objective, we propose a bilinear ADMM with an efficient single-step fixed point iteration for F step. Also, RED-PSM is guaranteed to converge to a stationary point of the proposed objective. The RED-PSM framework is composed of the denoiser pre-training on static slices of similar objects and the inference stage where the object is recovered from its undersampled time sequential measurements. Thanks to the static supervised training, RED steps are agnostic to the specific motion. Accuracy benchmark is the ground truth object at each frame, and we use bit reversed angular sampling for all scenarios. RED-PSM is compared with full PSM objective with total variation penalty and TDDIP, which is a recent deep image prior based method. RED-PSM mostly overperforms the best case TDDIP performance for all metrics for different numbers of projections P. The PSNR improvement over TDDIP increases with P, and the improvement is more significant for other metrics. Noting the wide range of metrics for different P, we provide a more detailed comparison with average TDDIP accuracies in the table. RED-PSM is also significantly faster than the compared techniques. Reconstructions and absolute errors for different objects at different times show that RED-PSM improves over the other methods, providing sharper results compared to PSM-TV and suppressing artifacts further compared to TDDIP. Similar better results are valid for RED-PSM for the reconstructed XT slices shown by the yellow line. Also, the PSNR versus time plots show the consistent better performance of RED-PSM. RED-PSM also overperforms TDDIP with different latent representation schemes on a cardiac DMRI dataset using multiple projections at a time. In this work, we propose the first PSM-based approach to dynamic imaging using a pre-trained RED-based spatial prior. To solve the final objective, we propose a novel and effective bilinear ADMM algorithm. RED-PSM is supported by theoretical analysis with a convergence guarantee. RED-PSM provides better reconstruction accuracies and significantly faster runtimes. The method is scalable thanks to a patch-based implementation with almost equivalent performance.